in-person speakers and Biocaml. Thank you.
Hi, thanks all. So I'm here to present on Biocaml, which aims to be a standard library for bioinformatics written in the OCaml programming language, which I'm guessing most of you have not heard of. So I'll spend a little time introducing OCaml generally, but mostly try to focus on Biocaml specifically. Sebastian Monde, who's the second author, is also here in attendance, so please seek him and me out if you have further questions. So first of all, OCaml is a multi-paradigm programming language. It does support imperative programming, which is the kind you know and love. It also has a very actually advanced and very high-quality object-oriented programming system. But first and foremost, it's a functional programming language, and that's really why you would choose to use it, is if you're interested in functional programming. It has several compilers. OCaml C compiles to portable bytecode. But for bioinformatics work, since we're always interested in high performance, you pretty much will never use that one. You're going to use OCaml opt, which compiles to native code. And it's a very well-supported compiler, and basically all standard architectures are supported. Very interestingly, OCaml also has a compiler to JavaScript. It's a very mature compiler that's widely used and generates high-performance JavaScript. So you can write in a statically typed compile language, but then generate JavaScript and run code on the client side. In addition, there are two more less mature but rapidly evolving compilers. One is OCaml Java, which compiles OCaml to the JVM, and Mirage, which is probably one of the most exciting projects, I think, period, generates not code, but it generates whole virtual machines. That's another project which we won't talk about. Just to let you know that it's a mature language that's industrial strength and not nearly as widely used as any other language, but is widely used. So for example, Facebook's new Hack compiler is implemented in OCaml. Citrix, which is responsible for a significant percentage of the world's virtualization infrastructure, is a big user of OCaml. And Jane Street, which is a high-frequency trading firm, writes virtually every line of code they have in OCaml, and they trust it for high-performance trading of billions of dollars per day. But also, it is also used in biology. Maybe these users you care a little bit more about. It actually has been used in projects behind the scenes in biology. So, okay, let me just show you some code so you get a little idea of what OCaml looks like. This is just a script. This is in script mode. So OCaml script is just a little program that lets you set your file to an executable, and you can just run it. At the top, we just give some flags which tell the compiler what libraries we want to use. And then I'm just opening up a bunch of modules so that I can more easily use the components defined within those modules. This is the only real code here. Basically, I'm just calling one of the Biocaml functions in a module called SAM, which reads SAM files. And I give it the first argument of the command line as an input. And the little, let's see, does this mouse work? Yeah. So that symbol is basically analogous to the Unix pipe symbol, but of course it's an OCaml operator, so it's strongly typed and much more high performance. And then what you get from the sam.readFile function is a stream. So the file gets read in a streaming fashion, and sequence is just a stream-like data structure. And you get the stream of lines from a SAM file parsed, right? And all I'm trying to do here is count the number of alignments, right? This is simple toy code. So initially, you have your count is 0, and then you give an anonymous function, which will be given each item of the SAM file one at a time, and the accumulating counter that you're trying to compute. So I match on the item, which is just like a case statement in other languages. In OCaml, it's called match. And every item is either a header item or an alignment. If it's a header item, I just return the count unchanged. If it's an alignment, I increment the count by 1, and then I print an output. So that's it. You can run the file, and it prints out the number of alignments in this code. So we have several more modules. Mostly on the left you see the library largely consists of parsers and printers for a wide variety of data formats. In addition, we do have a fairly decent amount of data structures for working with genomics data. especially dealing with integer intervals. We do have an Entree data client, and we're starting to work more on providing access to various data sources that are publicly available. I'd like to cover two of the highest level sort of API decisions we had to make in in Biocaml, which we've come to a decision on. One is error handling. Biocaml takes error handling very seriously. We don't like to just throw exceptions. We like to check for every single little tiny thing that a specification says and make sure that it's being handled. And we don't return a SAM alignment unless we've checked for every condition the SAM specification says should be met, right? So this has pros and cons. So on this side, a parse function returns an item from some string, but you know that it might not be able to, right? So what this function actually does is it throws an exception in some cases. The more strongly typed version of this returns something else. It returns item or error.t. Or error is a built-in OCaml data type. And what this does is explicitly tell you in the signature of the function that this function maybe throws an error. So there's pros and cons to both styles. If you throw exceptions, the API is much easier to use. But exceptions are a side effect, which is kind of anathema to functional programmers and makes parallel programming quite difficult. Also, you don't really see in your data types, your signature doesn't serve as documentation. On the other hand, on the strongly typed side, basically invert all of those, right? The pros are it is purely functional. The types do document the fact that an error can occur. And the cons are it's much more difficult to program with that, okay? So those are the use cases for those two styles. Exceptions are less safe. Maybe this is obvious to you, but I'll just give you a short example of what happens if we change 3 minutes. Okay, I'm going to skip this slide. Concurrency is the second main feature that we support in Biocaml across the board. On the left, we make blocking calls. On the right, we develop in a style where every single system call is called in a non-blocking fashion, and the entire library is built up with non-blocking calls. In blocking calls, the pros are it's easier to program this way. In the asynchronous case, the pros are that you might, depending on the nature of your overall program, might be making more efficient use of your system resources such as CPU and disk. Okay, again, it's much harder to do the asynchronous programming and much easier to do the blocking calls. So here's a big example of the two pieces of code, two styles being used to implement a demultiplexer. And here's some performance metrics. I'm actually showing you the opposite case. So the obvious case is that concurrency helps and makes your code faster. But also I want to point out that something's not true. So in this case, the drives the, in other words, what we have is a scenario where we really have conflicting objectives. Sometimes you want to just raise exceptions because it's just easier to program with that and easier to write simple scripts. Sometimes you want strongly typed errors. On the other hand, sometimes you want to make a blocking call, sometimes you want to program for concurrency. So Biocaml actually provides several different flavors to handle these different use cases. So we provide several libraries actually. An easy version is, as the name implies, meant to be the easiest to use, but maybe you're not going to get good high performance industrial strength code. The challenge for us as developers was how do you provide so many flavors of this code? So we came up with a solution. We actually implement a base library that's just called Biocaml. And due to a feature of OCaml called functors, we're able to auto-generate the two concurrency libraries that we support, and with very little work, generate the easy version. Parallelism is the part you all care about with functional programming. That's why it's becoming such a hot topic. I mentioned that since Biocaml is functional and most of the code is pure, it's dramatically easier to use it in parallel contexts. So for example, there's a library called parmap, which lets you parallelize code quite easily. If you have an array, let's say a very large data array, on which you want to apply some function to every element, the normal serial code would be this. You'd map f over every item in this array. Simply by replacing that call with parmap, you get a parallel version. These 2 lines of code are not pseudocode. This is complete, total OCaml code. That's literally all you have to write. Similarly, there's a library called async parallel, which is for distributed computing and works on multiple nodes. It has the concept of hubs, which are points of communication. You set up channels, and processes are basically jobs. And with very little effort, for example, we were able to write a toy example and get 4x speed up on a single node with multiple cores. But for parallelism, I'll just say it's a very complicated thing. There's a lot of work that has to be done, and OCaml is not going to magically make all your code go faster. Conclusions? So Biocaml, I think it's very easy to write easy code. That's really the main point I want to make. I think a lot of times when you start Googling for functional programming, you end up on a page about category theory. It's not relevant. It's not important. If you want to write simple code, it is simple to write simple code. And also, it's easier to write very sophisticated code. We have a lot of useful modules in Biocaml, but this is a library that's currently in a significant state of flux. We're basically rewriting the whole thing because we've come to a lot of decisions on the API. On the OCaml side, let me just say it's a good language. I hope you'll take a look at it. These are the only 2 URLs you need, and you can follow them for everything else. Okay. Thanks.
Thank you, Ashish. Any quick questions? I have one.
Yep.
One issue that comes up a lot with BioPython that I work with is that file formats may have good definitions, but people don't always follow them. And
Right.
being very, very strict is not always practical.
Right. So in my abstract for this talk, I mentioned another thing that I chose not to include in the presentation, which is we're providing a lightweight format specification system, which is inspired by MIME types. So you can say you have a SAM file, but then you can add some tag value pairs, right? And you can say, don't actually check that the reference sequence in each alignment matches one of the reference sequences defined in the header, right? So by specifying these little properties of your format, you're basically specifying variations of your format, and then our parser can take that into account and not check things if you care about speed.
Thank you very much. I think I should talk to you about the EDAM ontology, which sounds slightly related. Okay. Have a round of applause for our speaker, please. And Jojo.